So, do you have any questions for me from last class? All is good? So tell
I
me.
have a question. It's in my notes. I want to know how something of this worked. Like,
This is illegal.
like, I want to know why you had to do where this came from and why did you had to change.
Okay. How about we talk after class? Because I'll show you everything. Okay?
Okay, thank you.
Okay. So today the class is gonna be split into two pieces. The first part we're gonna discuss an algorithm. Okay? I need help of two people. What's your name?
Dawson.
Dawson. Do you mind if I use your name?
Sure.
Dawson. Yeah.
Ian.
Ian. Okay. So Dawson, Ian, and I decide to take a vacation during reading week, right? We go to a tropical island and we take a bottle of very expensive whiskey with us. And we decide we're going to drink it late at night by the fire, right? So when we arrive, each person goes do whatever they want. At night, we come back. We found that the bottle of whiskey is empty. So we start pointing fingers, who drank it. Nobody wants to confess, right? So after hours of discussion, we realize something scary. What if none of us actually drank the whiskey and there is somebody else on the island? So we decide to settle. We want a way where whoever drank it will just confess. We don't care who it is, we just want to know, is it one of us or not, right? So we try to come up with an algorithm, a way to anonymously announce to the rest of us that, okay, it's me, I drank the whiskey, right? So this is the problem we're working with. And this problem is famously called dining cryptographers, right? This is a very bad one. Right? So there are like a bunch of cryptographers and they want to dine on this bottle of whiskey. This problem is also called anonymous broadcasting. Okay? So we want to come up with a way that is not only applicable to humans, but also computers can do it. Otherwise, we could simply say, okay, we write on a piece of paper, whether we drank it or not, we put it in a box and we read. But it's not going to work for a computer, right? So we come up with an algorithm, which is this one, that works for this case. Let's see how it will work, right? So for now, we're going to switch our names with this. We're going to be called P1, person 1, person 3, and person 2, right? So what do we do? At first, each one of us will just choose a random bit. Each PI random bit BI, right? So person 1, which was a bit, B2, and B3, right? And that's the secret. Nobody else knows the bit. What do we do after that? Well, so let me just make it clear that BI is a bit, so it's 0 or 1, and it's a secret. Right? After that, each PI whispers their BI to their clockwise neighbor. Right? So, right now, P1 tells P2 its bit. So right now, P2 knows both B1 and B2. P2 whispers its bit, and now P3 knows B2 and B3, and P1 knows B1 and B3. All right? So after that, step number 3, each PI will calculate something. It will compute SI, right? Which is, it's the sum of the bits that it knows mod 2. Right? So what will this look like? You know what modulo 2 looks like. You should keep in mind this property, which is if you have 2 bits, 1 plus 1, and then mod 2, 1, 2, 0 plus 1, and 0 plus 0. Okay? So 1 plus 1, this is 0. This is 1, this is 1, this is 0. So whenever you sum up 2 bits that are equal, you're going to undo mod 2 is going to be a 0. If they're different, you're going to end up with a 1. Right? So now, S1 is going to be what? What does P1 know? It knows B1 and B3. Mod 2. S2, what does P2 know? B1 and B2. B1, B2, mod 2. S3, we check which 2 bits does P3 know. It's B2 plus B3 mod 2, right? And these are still a secret. So the only person that knows S1 is P1. The only person that knows S2 is P2. S3 is P3. Right? So now you will calculate something else. This is step 4. Yeah, 4. Now again, each PI computes a bit Ti, right? So here's the thing. If Pi is the person that drank the whiskey, okay? If this is the case, then Ti equals Si plus 1 mod 2, right? This one, let's call it just B, right? Otherwise, Ti is going to be equal to Si. Okay? You follow so far? So now, step 5, each person announces their Ti. Okay? So now what do they know? This one knows T1, T2, and T3. This one knows T1, T2, and T3. This one knows T1, T2, and T3.
What does T represent?
It's just a bit. You calculate it using this way, right? So let me just, okay. Okay, let me finish the last step and we'll go over it, right? So and then, each person computes the following. T1 plus T2 plus T3 mod 2. Okay? And the claim that we're going to make is this, that this number, T1 plus T2 plus T3 mod 2 is going to equal 1 if and only if someone drank the whiskey. And when we mean someone, it's one of us. Me, Dawson, or Ian. Okay? And this one is actually this B that we talked about. So, let's go over the whole thing again, right? So we have 3 people. At first, each person will basically pick a random bit, a 0 or a 1, and it's a secret. But then, each person will whisper only to their clockwise neighbor the value of their secret bit. So if you start with P1 knowing B1, P2 knowing B2, P3 knowing B3, after that, P1 will know B1 and B3, P2 will know B1 and B2, P3 will know B2 and B3. After that, each person will just compute the sum of the 2 bits that they know, modulo 2, right? So they calculate S1, S2, S3, which are still a secret, right? Then, each person will calculate TI, which is as follows. If I am the person that drank the whiskey, my TI will be my SI plus 1. Otherwise, my TI will be SI. After that, each person will announce the value of their TI to everyone. So as a result, everybody knows the values of all the TIs. And then each person will compute TI plus T1 plus T2 plus T3 modulo 2. And the claim is, this thing will be equal to 1 only if it's one of us that drank the whiskey. Otherwise, it's going to be 0. Okay? So let's verify that. Now, remember this. If 2 bits are equal and you add them up, then you do modulo 2, you're going to get a 0. And if they're not equal, you're going to get a 1. So let's see, what does this actually look like? T1 plus T2 plus T3. Well, okay, from this point on, every statement I write is modulo 2. But to save space, we're just going to assume it's there, right? Right? So, what is T1 plus T2 plus T3? Well, T1, okay, is S1, which is equal to B1 plus B3 plus T2 is actually S2, which is B1 plus B2 How about we reach T3? T3 is S3, which is B2 plus B3. And assuming that one of us drank the whiskey, then one of us have already added B here, right? So we don't know which T is it, but one of them, if one of us drank the whiskey, then one of the T's will be the SI plus B, right? So what is this?
Are you missing B1, another B1?
Yes, I should be missing another B1. So B1, B3, B2. Let's just make sure. So T1. T1 is coming from S1, which is B1, B3. This is coming from S1. Now T2 is B1, B2. B1, B2. Okay? And then, this is where I missed. T3 is coming from S3, which is B2, B3. So this B3, B2 plus B, right? So this is coming from S3. So if you look at it, we have two B1s, right? And B1 plus B1 modulo 2 is definitely going to be 0. Because B1 is equal to B1, right? So it's either going to be this case or this case. But either way, whether B1 is 0 or it's 1, this will cancel with this, right? And the same for B3. I have a B3 here, and I have a B3 here. And because of the property of modulo 2, I'm always going to end up with a 0. And same with B2, it's going to cancel out, right? So what am I left with? I'm only left with B. Right? So since B is equal to 1, so T1 plus T2 plus T3 modulo 2 is going to equal to B. Right?
Why do they cancel each other out again?
Because of the property of modulo 2, right? So B1, BI plus BI mod 2 is always going to be 0, right? Because 0 plus 0 mod 2 is going to be 0. And 1 plus 1 mod 2 is going to be 0.
Why is it something different though, like 1 and 0?
Because it's itself, I'm adding the same number. How can it be both 0 and 1, right? Any questions? Because one of us drank the whiskey, right? So one of us had SI, but he added a B, right? Do you get that? So T1, T2, T3 equal S1, S2, S3, except for one person. And that one person had SI, and because they drank the whiskey, they didn't leave SI as is. They added 1 to it. You get that? So one of us who drank the whiskey, when they calculate TI, their TI will not equal SI. Their TI will equal SI plus 1 or plus B. Is it clear?
Would this still work if many people ended up drinking the whiskey?
Otherwise, well, in that case, it's not a secret, right? This works if one person drank the whiskey. But this generalizes to more than 3 people. So if you have a group of 10 people, but one person drank it, this still works. Not exactly like this, we can modify it.
Okay.
But the thing is,
How does everybody know if like two of the 3 people drank the whiskey? Like,
this way. We just showed that if only one person drank the whiskey,
Okay.
right? And we followed this algorithm, in the end, each person will know T1 plus T2 plus T3. And the only thing you need to do is add them up, do modulo 2. If you end up with a 1, then one of us drank the whiskey. If not, then there is somebody else on the island, and it's not one of us that drank the whiskey, right?
What's the extra B for?
This is to indicate whether you drank the whiskey or not. It's coming from here.
Oh.
You see that? So the person that drank the whiskey will add a B to their SI.
So this is based on only one person that drank the whiskey,
Yeah.
and everybody's telling the truth to the
Yeah, obviously. Everybody, we're assuming that we're too scared right now. We're not pointing fingers. Everybody's telling the truth, and only one person drank the whiskey. Okay? Yeah. You mean here? Yeah, this statement. But we're going to continue also, the rest of the proof is going to be mod 2.
So B indicates nobody drank the whiskey.
If B was equal to 0, then nobody drank the whiskey, and there's somebody else on the island. If B equaled 1, then one of us confessed that they drank the whiskey.
Ah, okay.
Is that clear? So what did we do so far? Because our algorithm needs 2 purposes. Number 1, communicate with everyone that somebody drank the whiskey. And the second part is anonymously. We need to ensure that this cannot be traced back, right? We need to make sure that using the information that each person knows, they cannot figure out who actually drank the whiskey, right? That's the whole point. Anonymous broadcasting. Okay? So the first part that shows that we successfully communicated the information that one of us drank the whiskey or not, we proved it using this, right? Because each person will have enough information to figure out that did one of us drank the whiskey or not. Is this part clear? Any questions? Okay. So now let's do the second part. Now we want to prove that if you do this, nobody can figure out who drank the whiskey, right? So we're going to start with this. Suppose, without loss of generality, that I am P2 and I didn't drink the whiskey. Right? So if I'm P2, what do I know? Well, P2 knows the following. I know B2 because it's the bit that I guessed. And I know B1 because P1 whispered their bit to me. And I know also T1, T2, T3. But not B3. I don't know B3, right? So in here, I have two cases. In the first case, I have B1 equals B2. Right? And this I can verify because I know B1 and I know B2. So I know that they're equal to each other or not. But I don't know whether B3 is equal to them or not. So also I will have two cases. B1 equals B2 equals B3. So in that case, if P1 drank the whiskey, right? Then what do I have? Well, if P1 is the person that drank it, then their T1 equals S1 plus 1, right? But what is their S1? It's B1 and B3. It means B1 plus B3 plus 1, right? But what is this equal to? I know B1 and I don't know B3, but I'm assuming they're equal, right? Because they're equal and they're modulo 2, they're going to cancel out, right? Because everything is modulo 2, which means T1 will equal 1 in this case. And T3 will be just S3, and S3 is what? It's B2 plus B3. But again, I know that they're equal, so their sum, modulo 2, is going to be definitely a 0, right? But it could be that P3 drank the whiskey. In that case, T1 will just equal S1, which is going to equal B1 plus B3, right? But I know they're equal, so their sum modulo 2 is going to be a 0. But in that case, T3 is going to be S3 plus 1, which is going to be B2 plus B3 plus 1, which is going to be equal to 1, because everything is modulo 2, and these two are equal. Right? But it could be the other case, which is B, which is B3 is not equal to B1, and it's not equal to B2. And that's possible, right? Because B1 is equal to B2. So B3 could be the other bit, the opposite bit. Well, in that case, we also have two choices. If P1 drank the whiskey, then what do we have? Well, T1, which I know, is going to be S1 plus 1, is going to be B1 plus B3 plus 1. But B1 and B3 are not equal, right? We just assumed that this is the case we're studying. So because B1 and B3 are not equal, then their sum modulo 2 is going to be a 1. Plus the 1 that's coming from P1 drinking the whiskey, the sum will be 0. And if it's T3, because P1 drank the whiskey, then T3 equals S3, which is equal to B2 plus B3. Again, B2 and B3 are not equal. This is the case that I'm assuming to be in. So their sum, modulo 2, is going to be a 1, right? Let's check the last case. So if I'm in this case, P1 could have drank the whiskey, but also could be P3, right? In that case, T1 will just equal S1, which is going to equal B1 plus B3. But because they're not equal, their sum modulo 2 is going to be a 1. And T3 will equal S3 plus 1. S3 is B2 plus B3 plus 1. Because these two bits are not equal, then their sum modulo 2 is going to be a 1. And I have another 1, so that's going to be a 0. So let's look at what this actually means. Okay? What are we trying to do with all these numbers? I am person P2. I know that I didn't drink the whiskey. And I know B1, B2, and T1, T2, T3. And I don't know B3. I'm trying to reverse engineer using these numbers to figure out who actually drank the whiskey. Can I figure it out or not? Well, I know if these two bits are equal or not, because I know both of them. So if they are equal, I have these. This is known, right? To me. But this and this are not known to P2, right? So I don't know whether I'm here or I'm here. So I'm going to try to guess. Well, if B3 was equal to B1 and B2, I just try to do the math. Then if P1 drank the whiskey, then T1 will be S1 plus 1. And this is what S1 is. Then I'm going to get a 1. And T3 is going to be a 0. If P3 drank the whiskey, then T1 will be a 0. And T3 will be a 1, right? But I'm not sure. I could be in case B, where B3 is not equal to B1 and 2. And in that case, if P1 drank the whiskey, then T1 will be a 0 and T3 will be a 1. And if P3 drank the whiskey, then T1 will be 1 and T3 will be 0. So do you see a pattern here? Anybody sees a pattern? Okay. The pattern is, this is an absolute mirror from each other. What does this mean? I don't know if I'm in this case or in this case. But if I am in this case and P1 drank the whiskey, then T1, T3 will be 1, 0. But if I'm in this case and P1 drank the whiskey, then I'm going to get 0, 1, not 1, 0. But I don't know if I'm here or here. See, they're absolute mirrors from each other. And again, if P3 drank the whiskey, if this was equal to them, then this is going to be a 0, 1. But if it was the other case, then it's a 1, 0. So I cannot tell using T1 and T3. Think of it like this. I know T1, T2, T3, right? I know this. So I know I'm in case 1. So I will look like this. I will say, because I know T1 and T3, if they're 1, 0, right? Let's say they're 1, 0. I'm trying to guess who drank the whiskey. If they're 1, 0, it could be that the first person drank the whiskey, because they're 1, 0, right? It could be that the first person drank the whiskey if B3 was equal to them. But it also could be that the P3 drank the whiskey if B3 was not equal to B1 and B2. But I don't know B3. So I cannot tell whether I'm in this case or I'm in this case. Which means I cannot tell whether P3 drank the whiskey or P1 drank the whiskey. Right? And if it was the other way around, if it was a 0, 1, I'm going to try to guess. Well, it could be that P3 drank the whiskey, which is this case, if B3 was equal to B1 and B2. Or it could be that P1 drank the whiskey, which is this case, if B3 was not equal to B1 and B2. But I don't know B3, so I cannot tell which case I'm in, right? Doesn't make sense. I know the math can be a bit annoying, but do you get the point? Like using my information here, I cannot tell who drank the whiskey. Any questions? You?
So when you're adding T1, T2, and T3, you're just adding T1, T3, but S1, you're adding S1 mod 2, right? So why
No.
are you not taking like mods there?
What do you mean once?
When you're calculating S1, you are doing T1 plus T2 mod 2. But then when you are taking the sum of T1, T2, and T3, you're not taking any mods there.
No, I'm taking it. Everything is mod 2. See this? Because if I do that, I won't have space to write on the board. So from this point onwards, everything is going to be mod 2. So assume that here there is mod 2, and here there is mod 2, here there is mod 2, and so on. This is just for space. Questions? Anything? Should I repeat? Anybody wants me to repeat? Okay. So we'll go over this just really quickly first.
T3 equals S3 equals B2 equals 0.
No, T3 is equal to S3 plus 1 because P3 drank the whiskey, right? If P3 drank the whiskey, then T3, based on the algorithm, will be S3 plus 1. And S3 is actually B2 plus B3, right? It will be 0. Why? Because B2 and B3 are not equal. So their sum modulo 2 will be 1. Plus 1 will be a 0. Right? Okay, I have 4 more minutes. Okay. I'll show you the mirror case. Hopefully that will make things clear. Well, this is case 1. What if it was the other? Tell me. No, I don't know. I don't know what B3 is. It could be, because I'm P2, and I don't know B3. It's a secret, right? Nobody told me what B3 is. It could be that it's equal to B1 and B2. It could be that it's not equal to them. Right? There is 2 cases. This is the whole point. I don't know B3. And because I don't know B3, I cannot tell whether P1 drank the whiskey or P3 drank the whiskey. If I knew B3, I could tell. Because I knew, am I in this case or am I in this case? But because I don't know, and the situation is mirrored, I cannot tell. Yeah, I will do this right now. So the other case would be this. The other case would be B1 not equal to B2, right? Because I know B1, B2. I could be in the other case, where they're not equal. Well, in that case, the first case will be, let's say, B3. Let me just follow my notes. So then, let's say B3 is equal to B1, and B3 is not equal to B2. Right? If I'm in case 2, where B1 is not equal to B2, then B3 has to be equal to one of them. And in that case, T1 will be, if P1 drank the whiskey, it's B1 plus P3 plus 1. What will that give me? Well, B1 and B3 are equal. So their sum will be 0. Plus 1 is going to give me a 1 again. But T3 is going to be B2 plus B3. But they're not equal. So their sum will be a 1. And in this case, if P3 drank the whiskey, T1 will be B1 plus B3. They're equal. So their sum will be a 0. But B2, T3 will be B2 plus B3 plus 1. B2 plus B3 are what? Not equal. So their sum is going to be a 1. Plus 1 is going to be another 0. And in the other case, B3 not equal to B1, B3 equals to B2. So how will that change things? Well, T1 will be B1 plus B3 plus 1. B1 and B3 are not equal. So their sum is a 1. Plus 1 is going to be a 0. B2 plus B3 are equal. So their sum, modulo 2, is 0. In this case, T1 is B1 plus B3. B1 plus B3 are not equal. So 1. Here, B2 plus B3 plus 1. B2, B3 are equal. So their sum is a 0 plus 1 is going to be a 1. So look at the mirroring in this case. It's the other way around, which means if my T1, T3 are 0, 0, well, I'll look. I don't know whether I'm in this case or this case, but if they're 0, 0, it could be that P3 drank the whiskey. I'm here if B3 was equal to B1. Or it could be that P1 drank the whiskey where B2 is equal to B3. But I don't know B3, so I don't know if I'm here or if I'm here. You get that? Or it could be, because I know these two, right? I know T1 and T3. It could be that this is 1, 1. Well, if T1 and T3 were 1, 1, it could be that P1 drank the whiskey if B3 was equal to B1. Or it could be P3 drank the whiskey if B3 was equal to B2. You get the mirroring that's happening? Okay, thank you.
Yeah, I see it. Yeah, I see
So any question?
So the only thing you don't know when you put off into the cases is
B3.
the B3, but like when you go into a case, like you can easily like determine which one, if P1 drank the whiskey or P3.
I'm not determining. I'm making a guess. I'm saying if.
But
Right?
the guess is happening at B3. Like when you go in a level to
Yeah.
like, you have enough information to like match what you have with.
Yes.
Yeah.
Yes,
So-
but because I don't know whether I'm here or here.
So in essence, if I'm understanding this right, if you guess, you have a 50% shot.
You can guess. Absolutely, you can guess, but you're not going to have any information. You can't know for sure using these, right? You cannot use these to figure out who drank the whiskey, P1 or P3, because the cases are all symmetrical based on the information you don't know. Any more questions?
So in case 2, T1, T3 was either 0, 0 or 1, 1.
Yes.
And then in case 1, it was either 0, 1
Or 1, 0.
1, 0.
Yeah.
And why was that?
It's because of the way that this was calculated. You know what I mean? I can show you after class, but don't overthink it. I know these 2 bits. If my 2 bits were equal to each other, then these ones will have opposite bits. If these ones were not equal to each other, then these ones will have the same bit. It's just how the addition will work out. This is how the algorithm is working out to ensure anonymity. Is it clear? Okay, because if it is, this will be the end of the first half of the course. We're going to start now something completely new. Okay? So now we're going to study probability. And we're going to start with something a bit boring, which is definitions. But it is extremely important that we define everything that we're going to do. Because in probability, we're going to have, tell me. You know I can't answer that, right? Just try to get it. Pat is not going to ask you to write this. The midterm is multiple choice. So, in probabilities, the reason we're defining everything because we're going to have so many different examples where if you follow your intuition, you're going to make a mistake. Things are going to be counterintuitive in so many different examples. So that's why we need to ignore intuition in many cases and just follow the definitions and follow the math, right? I'll start with a few definitions, then we're going to do some fun examples, and let's see how much time we'll have. So, what's a sample space? A sample space is an unempty countable set. So a sample space could be anything. It could be a set of heads and tails. It could be a set of 0, 1, 2, 3. Let's not make 0. Let's say it's 1, 2, 3, 4, 5, 6. Which is like the faces of a die, right? So both of these are a sample space. Now, each element in S in a sample space S is called an outcome. And each subset is called an event. Right? So, which means that this is an outcome of S. And this is an event in S. Okay? There's just so we can agree on the terminology. Now, a probability function is this. Is a function call it PR, probability function. It's from S to R, such that it meets two conditions. Right? So for any W in S, the value of that W outcome is going to be between 0 and 1. And the sum of all outcomes over S, sum of their values, is going to be a 1. Okay? And we will call this will say that PRW is the probability that outcome is equal to W. Right? So I think this is the last definition, which is a probability space. A probability space is a pair that we just defined. It's a pair S, PR, where S is a sample space and PR is a probability function on S. Right? So the last rule is this. For any subset of the sample space, we define the probability of A to be the sum of the events, the outcomes that are in event A. Right? Are the definitions clear? They're just straightforward. We need them to down.
So you're just saying like you have a sample space of like, let's say 5 numbers.
Okay.
You're just saying like all the probability of those 5 numbers added together is 1.
Yes.
So this is just
This is just the definition of what a probability function is.
Total probability.
Yes, if the summation was not a 1, then it's not a probability function. Right? So now let's do examples. So we're going to do 2 examples, I guess. One on a coin, one on a die. So what would be the sample space if we were tossing a coin? Well, it's 2 things, right? A head and a tail. Let's see. Example 1. Flip a coin. Right? So what would be the sample space on the coin? Well, the possibilities are either a head or a tail, right? And if we're assuming that this is a fair coin, then the probability of head will be equal to probability of tail. It's going to be 1/2, right? So if we just use that definition that we just had, if I said, what is the probability of getting a head or a tail? Well, it's the probability of getting a head or plus the probability of getting a tail. It's going to be 1/2 plus 1/2. Right? This is all pretty simple. What happens if we toss 2 coins? Flip a coin twice. In that case, what's my sample space? Well, I'm either gonna have a head, then a head, head, then a tail, tail, then a head, or a tail, then a tail, right? And if the coin was fair, then the probability of getting a head, then a head, for accuracy, let's just leave it like this. The probability will be equal to that of a head and a tail, tail followed by a head, or tail, tail. It's going to be 1/4. Okay? So now we're going to do something slightly harder, which is this.
Does order matter in that case?
What do you mean?
Like getting a head and tail and head under the same thing?
Well, it's not the same thing, right? The way I'm recording it is I toss a coin and I record what I got. And I say the first coin was.
So the order does matter.
Yeah.
Right.
That's why I have different. That's why I deleted the set. Because if I put the set thing, then the order wouldn't matter. Perfect. Sure. Let's do this example. If I had a 6-sided dice, twice, what would be my sample space? Anybody wants to make a guess?
36.
Yes, but this is the size of my sample space, right?
It would be 6 squared, so 36.
Yes, but that's the size of my sample space. You know, the size of S will be 36. True. But my S will be this I, J. It will be a pair of numbers where I and J both are in the set of 1, 2, 3, 4, 5, 6. You see the difference? What do we mean by the size of the sample space and the sample space? And my probability function will be for any pair ij will be 1 over 36, right? Because the size of my sample space is 36. All the events are equally likely, so I'll get this for all ij in the set 1 all the way to s, right? Let's define something a bit more interesting. Let ak be the event that the sum of the two rolls is k, right? What would be A4? What kind of outcomes would belong in this event?
3, 1, 2, 2.
Okay, and 1, 3. 3, 1 and 1, 3. Yeah, okay. So 1, 3, 2, 2, and the 3, 1. So what is the probability of A4? Well, it's the probability of getting a 1, 3 plus probability of getting a 3, 1 plus the probability of getting a 2, 2. Right? Well, what is the probability of getting 1, 3? Well, it's 1 over 36 plus 1 over 36 plus 1 over 36. You're going to equal to 3 over 36, which is 1 over 12. Okay, so in this case, we chose the number 4, which is slightly easy to count. But if we use number 11 or 9, you might miss some of the outcomes that would give you, that would belong in that event. So let me show you one way to do it. So let's do 1, 2, 3, 4, 5, 6. And let's say this is J. And this is I. It's 1, 2, 3, 4, 5, and the 6. Then this would be 2. This is their sum. 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, and 8, 4, 5, 6, 7, 8, and a 9, 5, 6, 7, 8, 9, and 10, 6, 7, 8, 9, 10, and 11, 7, 8, 9, 10, 11, and 12. So what you can do is this. If you draw this, if I tell you, well, which sum will give you, what was our example, 4, you can see. This is my sample space, by the way. Right? The sum of everything, I'm sorry. This is all the possible outcomes. I could have A2, or A3, or A4, or 5, or 12. But there is no possible sum that I could get that's out of here, right? So if I tell you what's A4, well, you can check. I have 3 times. So it's 3 over 36. Let's try to solve a lot of them. So what's PR of 2? I'm sorry, let's write it properly. It should be A2. Well, there's only one of them, right? It's 1 over 36. What's the probability of A3? Well, it's 2 over 36. How about A5? Well, 1, 2, 3, 4. It's going to be 4 over 36. Probability of A6. Count them, 1, 2, 3, 4, 5. That's going to be 5 over 36. PR of A7, that's going to be 6 over 36. Count the 7s, you realize you have 6 of them. PR of 8, Now we have some kind of symmetry here, which we're going to have 5 over 36. PR of 9. We're going to have 4 over 36. PR of 10. It's going to be 3. 1, 2, 3. 3 over 36. PR of A11 is going to be 2. PR of A12, 1 over 36. This is clear, right? So, now, trying to do everything like this is extremely inefficient if you want to enumerate all the possible events in a given, all the possible outcomes in a given event. So, we will try now to have a set of rules that are very similar to the ones we have in counting. They're very similar to the sum rule, the complement rule, the principle of inclusion-exclusion, but they're going to be applied to the case of probabilities. So, what is the probability of the empty set? Well, it's going to be the sum of the outcomes in the empty set, right? But since there are none of them, so it's going to be a 0. We call two events disjoint. Let's call them A and B if, because the events are sets, right? If the intersection is the empty set. And in that case, if A, B are disjoint events, then just like the sum rule, the probability of A and B is going to be the probability of A plus the probability of B. Right? Well, what if I have more than two events? If I have A1 all the way till AN, and they are pairwise disjoint. Okay? Then the probability of A1 union A2 union AN, that's going to be just PR of A1 plus PR of A2 plus PR of AN. To make sure things are clear, pairwise disjoint means that any pair of them have 0 overlap. So AI overlap with AJ is going to be equal to the empty set for all I that's not equal to J. Let me write this like this, which is the sum of I equals to 1 until N PR of AI. Then, can we use this rule to solve something like this? What is the probability of A2, A4, union A6, union A8, union A10, union A12? Well, what does this mean? This means that what is the probability that if I throw a dice twice, I will either get, the sum will be either a 2 or a 4 or a 6 or a 8 or a 10 or 12. Well, this is clear that all of them are pairwise disjoint because the outcome, the total, cannot be both a 4 and a 6 or a 6 or a 10. The sum is just the sum, right? So these are all pairwise disjoint. And because I calculated each one of them over there, this is going to just be the sum. Let's write it like this. This is going to be the probability of A2 plus A4 plus A6 plus A8 plus A10 plus A12. What do you think this number would be? If you sum all of these, you're going to get, well, the sum will be 1 over 2. Right? The last example for today will be to try to do this in a different way. Okay? Can we solve it using a different way, but still using this pairwise disjoint kind of thing? Well, if you look at the set that I have, the sum is always even, right? So when do I get the sum to be even? Well, it happens I plus j, which is the number that I'm interested in, right? So if it was a 4, then I plus j is 4. Is even if I is even and j is even. Or I is odd and j is odd. So because that event that I had was basically all the possible even outcomes that I could get, right? 2, 4, 6, 8, 10, 12, then I could say the probability that I plus j is even is equal to the probability of I odd and j odd, or I even and j even. These are disjoint, right? A number cannot be both even and an odd at the same time. So as a result, we can use the rule to say that these two things, we can just add them up because there is no overlap. So this will be the probability that I odd and j odd plus I even plus j even. What is that? Can you make a guess? Don't try to count. Can you try to find it in a different way? I have 36 possible outcomes, right? And I have, because I have 1 to 6, and I have 1 to 6.
Exactly half.
Yes, but what about this? This is going to be a quarter, right? Because a number will just be even, even, or odd, even odd, and odd, odd, right? The I and the j. But because we know from 1 to 6, we have 3 numbers even and 3 numbers odd. So this will be 9 over 36. This is going to be the quarter, right? And this is also going to be a quarter. If you don't see it, you can just verify it. You can basically say, okay, when do I get both I and the j as odd numbers? So this is one of them. 2, 3. Then you come here, 4, 5, 6, 7, 8, 9. That's it. So 9 over 36. And you do the same for the even. Any questions? So Pat is going to come next week, and he's going to take it from this point on. So if you have questions, I think we have some time. Nothing?
Can you just go over that last part again? How you
This? So I'm saying the numbers are like this. The numbers I and j either could be even and even, odd and even and odd, or odd and odd, right? And in my set of possible outcomes, I have numbers from 1 to 6. From 1 to 6, I have 3 of them even, 3 of them odd. And they're all equally likely, right? So this is going to be 1 over 4. This is going to be 1 over 4. This is going to be 1 over 4. 1 over 4. Does it make sense? You can use anything you want, as long as you get it done. Questions? I think. If you have questions, we have time. If not, we can stop at this point.